Thank you for the introduction. Morning, everyone. It's a great honor to be here to share our recent study on the development of seawater mixed ultra high performance concrete UHPC for additive manufacturing. So we just started this test for the past year, so it's still in the initial stage, but it's my great honor to be here to share our progress. And this study was mainly done by my Ph.D. student, Mr. Mohammed Mustafa. And he's not here today, so I just present on behalf of him. So I think UHPC is not a new concept to most of the people in this room. So it has very exceptional properties, but on the material level, the main difference between UHPC and the conventional concrete lies in a few items. For example, it uses lower water to cementitious material ratio. It has the high volume of cementitious material using fine sand, typically no gravel, but some study use gravels as well. And it used micro steel fiber, and some study used synthetic fiber as well. And to maintain the good or desired fresh properties at such a low water to cementitious material level, typically they use high dosages of chemical admixture, for example, superplasticizer. So the difference in the material level result in different properties. When we compare the conventional concrete, UHPC shows greater or more densified microstructure. It has the greater surface quality with less defects on the surface, like micro cracks or capillary pores or other defects. As a result, the permeability of UHPC is much lower than conventional concrete. Typically, it's 10% or even lower than that of the conventional concrete. And the compressive strength is typically 4 to 5 times higher. And of course, as you can see from the last figure on the right-hand side, it has better ductility and higher toughness to be ruptured. But of course, there are some other differences. For example, the higher cost. I didn't list it over here, but it's very well known. Yeah, due to the exceptional performance of this material, it has been used for many different applications. For example, for bridge structures like bridge deck, the joints or connection of the bridges, and pre-stressed girder, and even for the structural repair. In addition to the application in bridges, it can be used for other civil infrastructure, for example, tunnels, wind turbine towers, and earthquake-resistant structures as well. The two figures below over here, so I'm sorry for the small text. It shows the number of the construction project in the US, focusing on the highway bridge construction. As you can see, right after 2009, this is very small, this is 2009, there's a clear increasing trend. And within only 10 years, the number of the construction project for the highway bridges reached 70 across the country. Oh, sorry. Yeah, reached 70 projects across the country. And there's a slight decrease during the COVID-19 pandemic, but we can see it re-increased again. So the map shows the distribution of the highway bridge construction in the US. It is a long story to see how to design UHPC, but in summary, the key principle of the UHPC design lies in the maximization of the particle packing density of the material used in this material. As you can see from the first figure, if you used fine particles or large particles, right, so, yeah. Okay, sounds good. So if you can see, as you can see from this figure, right, so if you use fine particles or coarse particles, the packing density of the system cannot be maximized, right? So because the space between the particles are still there. So in order to improve the packing density of the particles in the UHPC system, we need to use multiple skilled material with well-designed or well-controlled gradation. So a quite straightforward and effective way to guarantee the optimization of the particle packing density is using the modified Anderson and Anderson model, and which can help you to determine the desired proportioning of the material selected for the UHPC. at the same time, it can reach the maximization of the particle packing density. So UHPC is great, right? So, but when we use UHPC for 3D printing, we need to consider something else. So this is the brand new research topic. Based on my understanding, only a few scholars in the US are doing 3D printing of UHPC. And the reason we use this for 3D printing is that there are some advantages. For example, the use of fine granular constituent. So there's no gravel, so the requirement for the nozzle head is relatively lower than the conventional concrete. And it has very high flowability in the fresh stage, so it can be easily extruded from the nozzle head. In addition to that, it has the strong cohesion and a high strength and a durability, making it ideal for the high performance of the printed structural element of UHPC. However, when we use it, we also face some challenges. For example, the ultra-low water to cementitious material ratio make it pretty hard to be mixed to reach the homogeneous stage. So typically, the mixing process is much longer than the conventional concrete. In the lab scale, at least it needs like 15 minutes. And the use of fiber is also one of the challenges, but based on my understanding, because UHPC use microsteel fiber, if we don't use the ultra high volume fraction of this fiber, so this is a minor challenge. So if we use large enough nozzle head. So if we want to tailor printable UHPC for additive manufacturing, we need to have rigorous balance between the fresh property and the post-print performance of this material. So the fresh property includes the ease of extrusion, the printability, and shape stability. And the post-print performance includes mechanical strength, the permeability, and durability to make sure that it is still on the level of the UHPC. So we studied many different formulations of UHPC in the past few years. But for the 3D printing, we just pick one formulation, gave us the highest strength, and from there, we studied the influence of two different chemical admixtures on the printability of this material. The first one is superplasticizer. The second one is the viscosity modifying agent, VMA. As you can see, we have three different levels of superplasticizer, starting from 1.93%, 2.17% to 2.41% by weight of the bender. On each level of the superplasticizer, we have three dosages of VMA, like 2.5%, 3%, and 3.5% by weight of the bender. So in total, we have 9 different mixes to make sure that we can find desired dosages of the chemical admixture to achieve desired printability of this material. But I want to emphasize that here is that we didn't use fiber because we use quite small 3D printer. The nozzle head diameter is only 6 millimeters. It's almost half of the length of the microfiber. So one of our future work is try to print this by using a larger nozzle head to see the influence of fiber on its printability. So this figure shows the whole mixing process. It takes about 15 to 20 minutes to get the homogeneous UHPC. The first test we did is the flowability. So we have a rheometer, and we have other approaches to determine the fresh property of the UHPC. But we just found that, the flow table test, according to 1437, is a quite straightforward way to make a short list of the UHPC to guarantee the printability. So considering the time after we finish the mixing and transfer the material from mixer to the 3D printer, which take about 10 to 15 minutes. So we just narrow down this time window. And based on our experience for this UHPC formulation, flowability in terms of flow diameter between 135 and 150 can give us quite good printability. So we just narrow down our study by studying M1, M2, M3, and M6. So in order to confirm our finding, we did the extrudability test by printing a single straight line. And so we have multiple repetitions for each group. But you can see, I just show most representative filament from each group over here for comparison. You can get a very clear idea that some groups like M3 has discontinuous segments over here. That means it's not good. And some mixers like M9, it is overflowed, over-extruded, so it's not good as well. So in order to get a better idea to select the right mixers for our future or further investigation, so we did the imaging analysis to compare the real filament with the desired filament with a width of 6 millimeter, which is the opening diameter of the nozzle head. So we compare the difference in the printing area of the filament, and we get this. So as you can see, M2 and M6 use the smallest difference between the real filament and the desired filament. So we focus on these two groups for the further study. And the next test we did is the printing. This is our nozzle head. As you can see, you can get a rough idea about the printing process. So we print a hollow cylinder sample with a diameter of 150 millimeter at a printing speed of 20 millimeter per second and a layer thickness of 2 millimeter. So this is a quite rapid printing because for each deposit layer, the effective time for the operation is only 24 seconds. So this is very ambitious. So if we can have a longer operating time for each layer, we believe we can achieve better printability. At least it can get stiffening and setting better. So we also quantify the maximum layer for each group to reach and until the collapse. As you can see, fortunately, the two groups, M2 and M6, which use the best extrudability, give us the highest number of the layers during the printing. So there's no other reason that we can give up. So just to focus on these two groups because both extrudability and printability are quite good. And what about seawater? So we know that UHPC is printable, right? But when we use seawater to replace the fresh water in UHPC, so something will be changed. So the high motivation behind this is that 97.5% of the water on Earth is seawater. So if we face the challenge of the fresh water scarcity, and if we want to do the 3D printing work for the coastal infrastructure, right? So using seawater is a quite promising approach. And seawater, the difference between seawater and the fresh water is a high concentration of the ionic species like chloride, sulfate, calcium, and magnesium, and so on. So this source can result in some changes in the cement hydration and the performance of the cementitious system. For example, the acceleration of the cement hydration. Due to the high hydration rate, so the viscosity was changed. And also, we can get a slightly higher early age strength in the presence of seawater due to the accelerated hydration of the cement. However, there are also some uncertainties for 3D printing. For example, the potential strength reduction at later ages, as mentioned in one of our previous presentation, and also the salt crystallization and changes in the pore structure, the changes in the rheology at a higher mature age. So what we need to do is to run a kind of investigation to optimize the mixer design by using seawater. In particular, the aim of this study is try to find a way to determine the right amount of the chemical admixtures to make sure that it has a good printability and a good post-print performance. We use real seawater. The seawater was collected from Roberts Beach in Delaware. And the time we collect this water is December 23, 2025, a day before the Christmas Eve. And the temperature, if my memory is correct, the temperature is between 20 and 23 degrees Fahrenheit. It's under the freezing point. And this is Mr. Muhammad Mustafa. So you can see such a professional doctoral student, right? So even he has bare feet in freezing seawater, he still keeps smiling when I take the picture for him. So, and right after this, we discuss it. So I promise that he can use this photo for his dissertation defense presentation. And then I talked to him that, so why don't we just use it earlier, like at ECI? So he agreed, so I can use this photo for this presentation. And research is not easy, huh? So we study the flowability and ship stability of the fresh UHPC. As you can see, the first two groups in the first figure, this is the fresh water UHPC, and all others are the seawater mixed UHPC. A clear difference between the freshwater UHPC and seawater mixed UHPC is the decrease of the flowability, right? So, and also from the stability, you can see there's no big change when we use the seawater. So this gives us a question, what is the best mixture design or the best dosages of the chemical admixture to guarantee the high printability? So we lower our expectation for the flowability between 125 and 140, and the ship stability is below 120 is the one we want to study, but we still have a lot of groups. So what we did is we studied extrudability. If you remember, I showed a kind of straight line for the freshwater UHPC, but here we print curved filaments for the seawater-based UHPC after different material ages, like 10 minutes, 20 minutes, and 30 minutes. And we also do the quantification of the area deviation between the real filaments and the desired filaments. As you can see, most of the groups show the under extrusion with increasing time, and the first three groups and the first four groups give us the quite good result. So surprisingly, the use of the seawater enhanced the durability. Different from the maximum number of 35 layers from our continuous printing of freshwater HPC, we can reach a pretty high number of layers of 146 for the seawater-based UHPC, which is quite good. So another work based on this is the deformation of the layers. Because we have so many layers, so what we did is to guarantee the accuracy of the analysis, we analyzed the deformation of every 10 and every 20 layers, and this is the result. As you can see, so the first 10 layers shows the highest deformation. This is understandable because it has over 130 layers above it. You need to support the weight of these layers. But the good thing is, even the highest deformation is still below 10%. So the retention of the deformation is about 91%, which is pretty promising. This is a fresh water, this is a fresh UHPC, not the hardened UHPC. Very quick, I know I'm reaching the time limit. So strength, we test the strength of printed UHPC by, okay, yes, we do. So by printing a beam and cut it into cubes, and we test the strength. Again, surprisingly, when we compare the mode cost for the control group is the mode cost and the printed seawater HPC, we get even higher strength from the printed one. That means the interfacial bonding issues from the regular concrete printing is not a big problem for this seawater-based UHPC. And the same thing we get from the flexural strength. As you can see, we have over 60% increase from the printed UHPC. So this is quite promising, and we are working hard to analyze the reason why this happened. And but if you go back to check the strength of the UHPC, right? So either the flexural strength and the compressor strength, it is much lower than the minimum requirement of the UHPC. So that is 17,500 according to Federal Highway. But here we only get 8,000, 6,000. We analyzed the reason for the low strength. A few reasons. First, we didn't use steel fiber. Second, we used high dosages of superplasticizer to guarantee the extrudability and the printability. And related to this is the a large number of the air voids in the UHPC. So we need to use something to mitigate this, for example, deformer. And that's one of our future work. So I would like to simply skip the conclusion. In one sentence summary, UHPC is printable. Seawater-based UHPC is also printable, even more printable. But there are still some challenges we need to address. Thank you.